Okay, so welcome to 446. This is the first real lecture. Just to give you a heads up, we're being recorded, but eventually this recording will be edited. Not everything will be talked about will go into the video. Just be relaxed. You're not even in the video. Only the board shows. So, just feel like this is a regular lecture. You have questions, raise your hand, ask. This is just don't be disturbed by the presence of the video. I am a little bit, to be honest, but I think we'll be able to handle it. So some of you guys missed the introduction, but if you have questions, just catch me after class. So essentially, what I want to do this lecture is I gave the overview of the course contact last time, and this time what I'd like to do is start with the course. And I like to do that by reviewing some mathematical preliminaries. So pretty much none of the stuff, well, except perhaps for one subtopic, none of it is going to be new. I'll talk about things like gradient, divergence, etc., curl. These are all things that you have seen before, but let's review it because it might have been a while since you last went over these topics. So I'll start with, therefore, a compact overview of, I'll say, common mathematical operations. Now, the common operations I am interested in are mostly differential operations, as I said, like divergence, gradients. But do not be discouraged by the presence of these operations. We're going to use them so many times again and again. Even if you don't like them, and it might be that you don't, you'll get used to them. And I'll review absolutely the essential parts of it so you will recall what they're all about. So the first thing I'd like to talk about is basis sets and vectors. So when we talk about a vector, probably the most popular vector one can talk about is the position vector. So I'll draw a coordinate system. Right. So this is our standard Cartesian coordinate system. And along the coordinate axis, I will define some vectors. I'll call them E1, E2, E3. Okay? So eventually, I will call these basis vectors. And then I will mark a certain position, let's say that point. And that point has a position vector x. Okay? And you notice that the vectors, I write a letter and I draw an underline. That's my notation for a vector. Another notation would be to put an arrow on top of it, but I prefer to put a line underneath. Okay, so this is the vector. This vector will have some components, let's say in the 1 and 2 directions. And it will also have a component in the, if I project it like this, in the E3 direction. So this is the x3 component. This is the x1 component. This is the x2 component of the position vector. So the basis set in our picture here, it is E1, E2, and E3. And this basis set, you notice that, so these are all unit vectors. They are perpendicular to each other. So this is our usual definition of a Cartesian coordinate system. So we have a Cartesian coordinate system. As opposed to what? As opposed to, for instance, a cylindrical or a spherical coordinate system. We're going to use those as well. We will have to. But first, let's go over all the fundamental operations based on the Cartesian coordinate system. OK, so once I have this coordinate system, afterwards, what I can do is I can express this vector using its components and the basis vectors in this Cartesian coordinate system. So I can write x is equal to x1, E1, plus x2, E2, plus x3, E3. Of course, it's sort of clumsy to write this sum explicitly. So often, I will prefer a summation notation, something like this. I equals 1 to 3 xi ei. Okay? Just notice that this I here is just any letter. So what matters is that I'm summing over I. It's 1, 1, 2, 2, 3, 3. So I could have just as well written sum over I equal, let's say j equals 1 to 3 xj ej. Whether it's an I or a j or a k, for me, it does not matter. What I will do additionally is I don't want to write every time that the sum is from 1 to 3 because more often than not, we will always be in three-dimensional space. So we know that the sum is going from 1 to 3. So I will simply write sum over j, xj, ej, for instance, okay, so that I skip some writing. All right. So let's go to a 2D example just to demonstrate a important point. So I will take a vector and I will first draw the vector. Now the vector, you know, you always hear what's a vector? It's a position vector or a velocity or an acceleration. It's something that we always hear has a magnitude and a direction. Okay? So let's say that this is our vector in 2D. And I will choose two different basis sets. The first one will be the original basis set. So let's call it E1 and E2. Okay? And let's say that this position vector is such that its components are 4 and 3. So if I go ahead and using this basis set, so I'm going to choose two. The first one will be E1, E2. Then I will choose something else. So I'm writing or there. And the first thing I can do is I can write x is equal to sum over I, xi ei. I'm expressing the vector with respect to its bases using its components. And then what I can also do is I can put the components of the vector and use standard linear algebra notation. This means that I take the vector x and I put its components in an array. I will still call it a vector. Okay, so this thing is now using the ei basis. It's 4, 3. Okay. Or let's first write x1, x2, it's 4, 3. Now, I will introduce another basis, okay? Because I'm usually free to choose a basis. And instead of choosing these two unit vectors as the basis, I will choose this direction as one coordinate direction, if you like. And instead of E1, I will call it E1 prime to indicate that it differs from the original choice. And then I will choose another direction that is perpendicular to E1 prime, and I will call it E2 prime. So I could express the vector with respect to this basis set or with respect to this basis set. The vector does not change. I'm just changing my basis set. And there are infinitely many choices, right? But I'm just indicating my choices with these two. So I could choose this basis set or the new one, the primed one. So now I can go ahead and express the same vector with respect to this new basis set. So I could write that x is equal to x1 prime, x2 prime. So the primed components indicate that I'm referring to the new basis, the other basis. And now the components are, right, it's 5 along the one direction, and it has no component along the two direction. So it's 5, 0. Okay. So the message here, just so you remember, we're going to come back to this point with a stranger object. The point here is that the vector, it's an entity. It represents something that is physical. But the components are the way the vector looks with respect to a particular choice of the basis. For one basis, it looks like this. For another basis, it looks like that. The vector doesn't change. Just the way it looks changes. Okay, let's keep that in mind. So I'll write here the way the vector looks depends on the choice of the basis. But it's the same vector. OK. Any questions so far? All right. So now let's proceed. So now we remember what a vector is. And in the meantime, I'm also, of course, introducing the way I note things, I denote things. So you'll get also used to that. All right. So now let's talk about operations between vectors. The first one is the scalar product. Sometimes you call it the dot product. So I'm going to make this summary as practical as possible. I always will try to give you some examples so that you both see what the concept was, you recall it, and then you also remember how to apply it. So let's take two vectors. And I'm going to choose a vector A, and I'm going to denote it with components AI. And then I will choose another vector B, has components BI. Okay? And then recall that we have the scalar or the dot product between these two vectors. What it means is that you simply multiply the components and sum them. So it's AI, BI. Another way to indicate this would be, right, you would take the components of the vector A, put them in an array. You would take the transpose of that, and you would multiply it with the components of B. That's another way to indicate this operation. This, remember, is the transpose. Transpose turns rows into columns and columns into rows, etc. So for instance, let's do one example. I will assume that the vector A has components 1, -1, 3. B has components 4, 4, -1. And then A dot B, right? So you multiply the components, and then you sum them. So 1 times 4, 4, -4, and then 3 minus 1, -3, so it's equal to -3. So that's the operation. All right? So now that we have a dot product, we're going to make use of it shortly. Let's go to the first differential operation, something that involves a derivative, and it is called the gradient. And you can take the gradients of many things. I'm going to talk about the gradient of a scalar. So let's first define a function. I think that's a good way to have a summary of this operation with an explicit example. So I will take a function. This function x indicates here the position vectors. So depending on where you are in space, the value of the function changes. It's just like depending on where I am in this room, the temperature changes. It's cooler there, it's warmer there, etc. Right? And I can write it like this. So the function depends on the vector, or I can write it explicitly. The function depends on the components of the vector. So these are two equivalent expressions. And here is the particular function that I will choose. And I will keep employing this function again and again in the next few subtopics. So let me check that I've written it correctly. OK. So we'll take the gradient of this function. Okay? And the gradient of the function, I will indicate it like this. Gradient phi, it's a vector. And let's say the vector is v. I'm just calling it v. It could be something else. I could have called it W, A, B, C. Doesn't matter. So v is equal to gradient of phi. It's a vector where the components are defined by del phi del xi. Right? So the ith component is given as the partial derivative of the function phi with respect to the coordinate xi. I will denote these in two alternative ways, this derivative. Sometimes I'll write it explicitly like this if I need that clarity. Sometimes I want to be fast, so I will put a subscript comma I, meaning that I'm taking a derivative with respect to the ith coordinate. OK, so therefore, we have the gradient of phi. It's a vector. I can put its components into a array like this. And let me calculate what this function is explicitly. Right? Let's do it together once. So the first one is del phi del x1. So it's 1 plus, this is 0, that's 0, 8x1, x2, 0, 6x3 squared, and then 7x2, x3. Right, and I can continue with the second one, partial derivative with respect to x2. That will give me the second component. So it's 2 plus 4x1 squared, 10 x2, x3, that's 0, and then 7 x1, x3. And then the third one, 0, 0, 3, 5x2 squared, 12x1, x3, and then 7x1, x2. Just let me know anytime if I happen to make a mistake. You can correct me. I just want to check this because we're going to use this vector. I don't want to have errors here. OK, looks fine. So notice that phi is a function of the position. I take its gradient, right? I still have a quantity, a vector, each of its components. It's also a function. So this is a scalar, which is a function of the position vector. This is a vector, which is a function of the position vector. So they are still actually, in some sense, functions. This is a scalar. This is a vector. So I could have written, for instance, v of x. That would be a way to indicate that. All right. So I've introduced the vector. I've introduced a dot product. I've introduced the gradient. Now let's recall something more, the divergence. The divergence, again, of a vector. OK, so I will take a vector. Let's call that vector v on purpose, because actually I'm going to make use of that v shortly. So I have vi, ei. That's the vector. Then the divergence, and I will indicate it as such. So it's almost like a gradient with a dot in between. That's a scalar. And let's call that scalar omega. So omega is equal to divergence of v, and it is defined as sum over I del vi over del xi. Okay? So you take the derivative of the ith component with respect to xi, and then you sum over those. So it's v1, if you like, v1 comma 1 in 3D, v2 comma 2 plus v3 comma 3. So continuing from above, or continuing with the vector that I had constructed here, let's calculate the divergence. So divergence of the vector. So I will take the first derivative, the first component's derivative with respect to x1, right? So 0, 8x2, 0, 0. Plus the derivative of the second component with respect to x2, 0, 0, 0, 10x3. And then the derivative of the third component with respect to x3, 0, 0, 0, 12x1. Okay, so that would be the divergence of the vector that I chose to be that vector, just as an example. All right. So we have the scalar dot product, gradient, divergence. What other type of operation is there for vectors? Curl. So cross product, some type of a cross product. So first, let's define the cross product, and then let's remember the curl. I will try, if I try to erase this board, remind me, I don't want to erase it. I want to keep it for a while. I'm going to make use of it. I want to make use of those numbers. So I'm erasing this board again. So the curl, the vector or the cross product. Okay. Now, there are different ways of defining this. So I will give you both ways, or at least two ways, let's say. The permutation symbol is something that I like to use. It's E, that's a standard choice, with three subscripts, I, J, K. Now, I, J, K, we live in 3D, so they are eventually going to be numbers like 1, 2, 3. I'm free to choose them. So this E, I, J, K, depending on my choice, could be E123, E223, E132, etc. Any three choices that you make. Okay? But the value of EIJK is fixed. Okay? So, and the value is a +1 if it is an ordered or an even permutation of I, J, K equals 1, 2, 3. Okay? I'll explicitly write this out after I summarize it first. So it's +1 if it's an even permutation of ijk equals 1, 2, 3. And if it is an odd permutation of this triple, it will be a -1. And it's 0 otherwise. Okay, so let me tell you what, well, maybe first I can give a short example here about what permutation means. So even permutation of ijk equals 1, 2, 3. So the idea is the following. You take ijk equals 1, 2, 3. First of all, no permutation is an even permutation, 0. Okay? So now even permutation means you take two numbers, switch their order, and you do it twice. So for instance, I can switch the order of 1 and 2, so it will be 2, 1, 3, but that's just one permutation. If I do it again, it will be two permutations. It's an even permutation. So 2, 3, 1. 2, 3, 1 is an even permutation of 1, 2, 3. Okay? So what else is? I can switch twice again. So I can switch these two, 3, 2, but then 3, 2, 1 would be an even permutation. So it's changing directions or the order 3 times with respect to that one. I need to change once again. 3, 1, 2. This is an even permutation. I switch orders 4 times with respect to that. So this is +1, +1, +1. If I had started here and switched only once, something like 2, 1, 3, it's an odd permutation. It's a -1. Anything else, it's 0. For instance, well, that means you do not obtain these 3 numbers by switching orders. You have to have some sort of a repetition. So for instance, 2, 2, 3, it's 0. 2, 1, 1, 0, etc. Now, the order actually, it's not very hard to remember. It is something that you can remember from the following diagram. I put 1, 2, 3 on a circle, and you then use the right-hand rule, okay? Because this thing defines cross product. I remember for a cross product, we had a right-hand rule. So if you rotate according to the right-hand rule, it's a plus. If you rotate in the other direction, it's a minus. Anything else, it's 0. So let's start, for instance. So I, J, K, right? So I rotate like this, 1, 2, 3. Or 2, 3, 1. Incidentally, this one. Or 3, 1, 2. 3, 1, 2. Okay? These are all plus 1. If you rotate in the other direction, for instance, I start at 2. Instead of going like that, I go the other way. 2, 1, 3. Or 1, 3, 2. Or 3, 2, 1. These are all minus 1. Everything else is 0. So for instance, again, that's 0. That's 0. Let's say that's 0, etc. So there are many more zeros than non-zeros. Okay? These are the only non-zeros, and this is the way you can remember that. Now the permutation symbol is nice because using the permutation symbol, you can define the cross product very compactly. And it will also allow us to define the curl operation somewhat more compactly. Okay, so let me erase this part first. All right, so I'll define the cross product. I'll take two vectors, A and B. Their cross product is a vector on C. And the components of C, they are given by. So now it's a bit lengthy because there are two summations over J and K. It's E, I, J, K. Okay. A, J, and K. So that's the definition, a compact definition of the cross product. Now, that's not the only definition. There is another definition. An equivalent but a different way to express the same idea. And that is defined through a determinant. So alternatively, and this is probably what you learned. So A cross B, it's a vector C that is obtained by calculating the determinant of the following. So you first take the basis vectors, you put them into the top row, and then A comes first, you put its components, A1, A2, A3, and then B comes second, so you put its components next. And then this indicates that I'm trying to calculate a determinant. Now let's also remember how to do that. So you would choose, for instance, a row, and then you would enumerate that or put a sign on that row, starting with a plus and then a minus and a plus. And then I'm going to calculate the determinant of the minor matrices and then appropriately combine them. So the determinant is equal to, for instance, a plus E1. And then you delete the row and the column. It would be the determinant of that. So it's A2B3 minus A3B2. Okay? And then delete the row and the column. E2, but it has a minus sign. Minus sign. And then determinant of what remains, A1B3 minus A3B1. Okay, and then the last one, plus E3. Delete the row and the column, A1B2 minus A2B1. So that would be the curl operation. Both operations are, of course, the same. So in other words, this and that, they are equivalent. So in other words, this permutation symbol essentially is allowing me to express this determinant very compactly. Okay, it's just in one line. And let's verify that it is so. So both are the same. So for instance, let's look at C1, just C1. So A cross P is a vector C, then this must be C1. This must be C2, and this must be C3. So I'm going to try to now verify that this is C1. It is consistent with that expression. So C, I equals 1, right? So it's I equals 1, sum over J, sum over K, E1, J, K, AJ, BK. So it looks ugly at first, but remember, there are so many zeros and so little non-zeros. So I start. So this is a 1. What can I pick? This goes from 1 to 3. This goes from 1 to 3. For instance, this cannot be 1 because it's 1, 1, it's 0. This cannot be 1. 1, 1, it's going to be 0. I can immediately forget about them. So terms like 1, 1, 1 also, they will die. So the only thing this can be, for instance, is a 2 or a 3. If this is a 2, this cannot be a 2, because then it will be 0. So it's either 1, 2, 3, or 1, 3, 2. Those are the only options. So this is equal to E1, 2, 3, A2, B3, or plus E1, 3, 2, A3, B2. Okay? So now, 1, 2, 3, it's a plus 1. 1, 3, 2, right? So it's 1, 3, 2, negative direction. It's a minus 1. So this is equal to A2, B3 minus A3, B2, which is exactly what I had. Okay, so the two are equivalent. It's just a different way to express the same quantity. All right. Any questions so far? All right. So I have only, let me say, we're halfway through. I'm going to show you this much more as a review, and then we'll move on with the actual course content. But I will make use of everything that I show here. So if you're not comfortable with any of the operations, come over and we'll talk about it. I'll also give you an assignment on these fundamentals. All right, so somebody said curl, and I said I first want to do the cross product. So let's proceed with now the curl of a vector. So I have the cross product defined there. Eventually, the operation looks very similar to a cross product, except instead of any vector, I have the gradient operator there. So the curl of a vector is a vector. Let's call that vector W. So W is equal to curl of V. And W is essentially, has a very similar expression to this. So I'm going to write EIJK. We are going to think of this thing as a vector with components partial x1, partial x2, partial x3. And this is the second vector. So instead of bk, I will write vk. This is going to be a partial xj. Okay, so partial vk, partial xj. This comes first. So if you like, think of it as the vector aj over there at the top. All right. So, of course, then alternatively, you can think of W as the determinant, just to follow up from there, E1, E2, E3. So use whichever one you find more convenient to remember. So you'll get the same result. So therefore, the result is what I already have written here. So it's E1. So this is like now, that's the first vector. So this is like V, so it's V3, comma 2, V2, comma 3. And then plus E2. So minus minus V1, comma 3 minus V3, comma 1. Plus V2, comma 1 minus V1, comma 2. Minus V1, comma 2. Okay. So now I will take the curl of this vector, okay? Just so we have one example, right? And I want to squeeze it in here because I have the expression over there. So for earlier V, which is equal to gradient of phi, for that example, let's calculate the components of the curl of the vector V. So that's equal to. Okay, so V3, comma 2, V2, comma 3. So V3, that's V3, right? Comma 2, 10x2 plus 7x1. Minus V2, comma 3. This with respect to 3. So 10x2 plus 0. No, plus 7x1. 10x2. There's a minus sign, so I put a minus in front of both of them. Okay. So that's the first entry. The second entry, 1, comma 3 minus 3, comma 1. 1, comma 3, 0, 0, 12x3 plus 7x2. And then minus V3, comma 1. 0, 0, 12x3 plus 7x2. And then the last one, V2, comma 1 minus V1, comma 2. 2, comma 1, 0, 8x1 plus 7x3. And then 1, comma 2, 0, 8x1 plus 7x3. I put the minus sign always because there's a minus sign there. And the result is not very exciting, right? It's a lot of operation, but the result is a clean 0 there, a clean 0 there, and a clean 0 there. Is that a coincidence? No, it's not a coincidence. Because the curl of a vector, which is the gradient of some function, is equal to 0. Okay? So I took the curl of a vector, which happened to be the gradient of a scalar function, and therefore there is such an identity. Okay? We will eventually at some point make use of this. All right, we have a little bit more time remaining. Well, actually, we have plenty of time remaining. So we can take a few minute pauses, right? Because we can always cut. We're doing 1 hour, 15-minute lectures, right? Maybe you're tired a little bit. So we can always take time and you can ask questions. Anything so far? Do not be daunted by anything. Okay, this is a fun course. Okay, so we have to do the math, right? So if you have questions, it's a good point. Are you able to follow? No challenge so far. Okay. If it's easy, then it's good. If it looks easy, it's good. All right. So now starts a little bit challenging part. Now I had to erase my favorite vector. We might actually need it. We'll see. If I need it, perhaps I will write it again. So now I'll draw a diagram to summarize sort of what we have done so far. We have taken a scalar to begin with. Of course, I defined the cross product and the dot product as well. But in terms of taking derivatives, I defined two operations. The first one was a gradient. And when I took the gradient, I obtained a vector. But what I could also do is I could take the divergence of the vector. That would take me back to a scalar. Okay. And what I could also do is I could take the curl. If I take the curl of the vector, I obtain another vector. Okay? So gradient sends me up to a vector, divergence sends me back to a scalar, but a curl sends me into another vector. Okay? So now I can do the same thing once more, right? So I can take the gradient once more. And what will I obtain? So it's a scalar. It's a 1 by 1, if you like. 1 by 1. 3 by 1. 3 by 3, right? It's going to be a matrix. So I put matrix on quotes for a reason. Okay, but let me write here a capital letter, which for me means something like a matrix. So if I take a gradient, I will obtain a matrix. I could take the divergence of that thing as well, and it will send me back to a vector. And believe it or not, you can take the curl of a matrix. And just in the same way, it keeps sort of the nature of the quantity. I will obtain another matrix. Okay? So the red part I've covered. The blue part I will start now defining. OK, so therefore, let's start with the gradient of a vector. Let's start with that part. So it's again a gradient, but this time of a vector. So gradient of V is a, I again put quote unquote, matrix. So when I take this quantity and the matrix I indicate with brackets, so these mean that I'm talking about the components of A. These are the components of, or before, well, the components of the vector in an array, the components of A in a matrix. Okay, that's what I'm trying to indicate with that. So A is gradient V. And because it's a matrix, it will have eventually two indices, every component. And it is defined as del Vi over del Xj. And therefore, if I build a matrix out of the components of A, so it's 1, 1, 1, 2, 1, 3, right? So it's V 1, 1, V 2, 1, 2, 1, 2, and then 1, 3 components, V1, 3, and so on. V2, 1, V2, 2, V2, 3, V3, 1, V3, 2, V3, 3. Okay. So that is the, well, actually, let's keep that here. Sorry. Just so we have the expression, and I erase something, for instance, this. And I have my favorite v, right, which was the gradient of phi. So I will indicate or give an example of the gradient of a vector using earlier v, grad phi. I erased it, so why don't I just write this, and then if you like, you can go ahead and check this at home. I'll just write the result here. You can also check on the fly with your notes, of course. You have everything on paper. Just to make sure that there's no mistake here. Okay. 1, 1, 1, 2, 1, 3. Let's say 2, 2, 3, 2, etc. Okay, fairly straightforward. Okay, so that's nice. Now, I want to mention something that's a little bit let me say, messy. It will sound strange at first because I'm pretty sure you have not heard it before. And so don't write for a while. If you want, you'll have time to write later. So the point will be the following. This thing is a vector, right? And I wrote this as well. This means the components of the vector v. Now, v is a physical entity. Okay. So let's say position, velocity, acceleration. It's a physical entity, magnitude, direction. Your choice of the basis will change the components, the way the vector looks in this array. But it's a physical entity. It's just looking different. The physics is not changing. Okay. So this is a matrix. But what sits inside the matrix, so just like here, this is an array. What sits inside is a vector. It's physical. This is a matrix. What sits inside for us will be always something that is physical. Okay? And this is a matrix, and therefore what sits inside will have a different name. We will call it a tensor only once. Just once I will use this notation to highlight this important point. And then from then on, because it's perhaps not the best terminology to use in an undergraduate course, and I don't want to overemphasize it, I will drop it. But once I want you to hear it. So A is a tensor. Now, just like the components of a vector, the way the vector looks is different depending on the choice of the basis. This is something physical. The way it looks in a matrix will depend on the choice of the basis. I will give you a very simple example. Now, for us, is this something meaningful? Do we deal with it? Indeed. Okay? You might be surprised, or maybe you're not surprised. Strain and stress, which is the nuts and bolts of this course, they are actually tensors. So in other words, the bases I choose eventually will dictate how the components of that thing in a matrix will look. Okay? Now, let me give you one example. Okay? Let's construct this example carefully. It is a mathematical example, sort of synthetic, but it will be sufficient to demonstrate the idea. So I choose a coordinate system. x1, x2. And on that coordinate system, or independent of the coordinate system really, I have a vector. This vector I will call v. Now, v is not just any vector. It's not velocity or something, but it has a special direction, and that special direction is it's at an angle of 45 degrees from either coordinate axis. Okay? And so now I can use this coordinate system, or I can choose another one that is perhaps simpler. This might be the one that somebody else prefers. something that is along the vector, one basis, and the other one, or the other direction, it's x2 prime coordinate direction. It's perpendicular to the other one. Okay, so I have given you two choices. Okay, so now I'll go ahead and express this vector. So this is a vector, v. It will have components v1 and v2. Okay, and I prefer or choose those components, right? So the angle is 45 degrees, so the components will be the same. Why don't I call them to be both x1? Just by chance. It's my choice. I chose it to be x1. They could have been x1 squared, whatever. What matters is that they are the same, right? So that's one choice. So for instance, it could be 1, 1, right? If I'm at location x1 equals 1, the value of the vector is 1, 1. Otherwise, it's a function of x1. Now, another way to indicate this vector is using the primed coordinate axis. So that would be v1 prime, v2 prime. Okay. So now it's going to be x1 prime, 0. Okay. So for instance, square root 2, 0. Right? So for instance, I am at, let's say this is indeed the point I'm at. And if this is 1 and that is 1, along that direction, 1, 1, it's square root 2. And the other direction is 0. So that's the example I picked. The components look different, but it's the same vector. Now, I will build a matrix, A. And this matrix will be the gradient of V. Okay? So it's the gradient of a physical entity, so it represents something physical. Okay? For instance, eventually this could be the displacement vector. Its gradient will give me something that is very closely related to strain. Okay? So it will be something physical eventually. But in this case, this is a synthetic vector, and it's just some matrix. But it's the gradient of that vector. Now, there are two ways I can calculate this gradient. The first one is with respect to the unprimed x1, x2 coordinate system. So aij is del vi over del xj. And that is easily written, right, as such. So 1, 1, so 1, 1, 2, 0, 2, 1, 1, 2, 2, 0. So that's A in the original coordinate system. Or I can use the primed coordinate system. In the primed coordinate system, it's the same physical entity A, but the coordinates will look different, or the components will look different. So I put a prime to indicate that. So aij prime, in other words, the appearance of the physical quantity A in the primed system is the derivative of vj prime, okay, because I'm in the primed axis, with respect to that primed axis, vi prime, over xj prime. Okay, let's again calculate it. So in this coordinate system, A looks like 1, 1, 1, 1, 2, 0, 2, 1, 0, 2, 2, 0. Okay. There is only one physical entity A. The way it looks depends on the choice of the basis, whether the original coordinate system or the primed coordinate system. Okay. So this will indicate, right, that eventually, for instance, if I'm talking about the stress, something that we understand, that we have used before, depending on my choice of directions, its components perhaps change. And this concept is not something that you are foreign to. Remember the Mohr circle? In the Mohr circle, you change the directions. And when you change the directions, you calculate new components of the stress. What you are mathematically actually doing is, without, we don't teach you this view because it's perhaps too impractical, too mathematical. But what you're really doing is you're calculating the components of the stress with respect to a rotated axis. That's what you're doing. Okay, so this is intimately related to Mohr circle. For stress, strain, Mohr circle. And let me also emphasize once again here that A is the same. The way it looks changes. All right. So whenever I write a matrix, actually we have to keep in our minds that it's actually just the representation of that quantity with respect to a particular choice of the coordinate system. We'll just keep in mind, but from now on I will never refer to A as a tensor. I'll always say a matrix. And I expect you to at least be able to remember that, that we are actually being a little bit careful and a little bit perhaps sloppy with the terminology. All right. So we're in good shape. Tired? A little bit maybe? Okay. So, all right. So, but we have still 15 minutes. And I will proceed now. What have we done? We have talked about the gradient of the vector. I will now talk about the divergence, and then there will be the curl as well. Okay, so we're almost done with this concept. Why don't I keep this thing here? This is the gradient of V. Let's keep that. So divergence. We've talked about the divergence of a vector, so now it's of a matrix. So when you take the divergence of a matrix, it sends you back to a vector. So let's call that vector, actually I called it A. A is equal to divergence of capital A. And the components of A, they are defined to be del Aij over del xj. And so that's the definition of a divergence. So for instance, A1 would be A11, 1 plus A12, 2 plus A13, 3. Right. So for instance, using earlier A, which is gradient of V. If I use this A, I can take its divergence now. So the components, they go into a vector. So 1, 1, 0. Sorry, 1, 1, it's 0 plus 1, 2, 2, it's 0. 1, 3, 3, it's 12. And then the second one, 2, 1, 1, 8, 2, 2, 2, 0, 2, 3, 3, 0. So it's only 8. And then the last one, 3, 1, 1, 0, 3, 2, 2, 10, plus 3, 3, 3, it's 0. So it's only 10. So in this case, it came out to be a constant. It's not a function anymore. All right. And we can finish up with a curl of the matrix. Now, among these, I find the curl of the matrix to be the messiest one. The other ones are relatively neat, but we will need the curl of a matrix. And therefore, this is very important. So now, the curl of a matrix, it's a new matrix, okay? And let's call it B. So B is equal to curl of A. Now, I will just give you the definition. The other ones, that's what I've also done. It's pretty easy to relate to in those earlier cases. Here it looks a little bit more complicated, but I'll just write it. So it's EMN. So I'll write it with some color so you can catch what is being summed over and what is not. So a little bit messy, but here let's see. It's component Bij, M and N I'm summing over, M, M, N, N. The third index of the permutation symbol is I. The first index of A is J. Okay? So that's B, I, J. Okay? So then you can go ahead and actually explicitly calculate how the components of B look. Let's do it for one case, one entry. I will write you the whole thing afterwards. So let us begin with entry 11. So if I'm looking at entry 11, so as an example, this is 1. This is 1. Okay? So that's also 1. This is also 1. Okay? So the messy part is this summation. So I will start summing. So it goes from 1 to 3. It goes from 1 to 3. But this is already 1. So the only combination that I can have is either m is equal to 2 and n is equal to 3, or this is equal to 3, that is equal to 2. Those are the only possible cases because everything else is 0. Okay? So E 2, 3 is one option, and I'm looking at I equals 1, so this becomes a 1. And then I will have A, J is also equal to 1. I'm in the 1, 1, and 3. 1. And then M is 2, N is 3. So this is 3, that is 2. It's one possibility, and the other possibility, it's a 3, 2, plus E 3, 2. This is a 1, A 1, 2, comma 3. Okay. So now if you do this carefully, and I suggest you do it just to sort of practice with this notation. You can obtain all the components. Okay. Actually, let me write it out. We have time. So this is E231. So it's 1, 3, 2. I'm writing it so you can, if you want, you can check with your own calculations. Okay, it's done. All right. Now, of course, for instance, 2, 3, 1, it's plus 1. 3, 2, 1, it's minus 1, right? So you can do some simplifications. So that is plus 1, minus 1. And let me go ahead actually write all of that. Plus 1, minus 1. Plus 1, minus 1. And then this is a minus 1, plus 1. Sorry. And then here is again plus 1, minus 1. All right. let me apply it to this example. Okay. So for earlier example, where A is equal to gradient of V, we have curl of A is equal to. Now, this takes a little bit of time, but again, let's do 1 together. 1, 3, 2 minus 1, 2, 3. 1, 3, 2, it's 7. Okay, 1, 3, 2. Minus 1, 2, 3. 1, 2, 3, 7. So plus 7, minus 7. So in this way, for every term, I will write what you would eventually calculate. Well, let's do one more together. 2, 3, 1 minus 2, 2, 3. 2, 3, 1 plus 7 minus, 2, 3, 2, 3, 1 plus 7 minus 2, 2, 3. Did I make a mistake? I do apologize. So let's look. 2, 3, 1. What is the problem? 2, 3, 1 plus 7, and then 2, 2, 3. There is obviously a mistake here. 2, 3, 1. 2, 3, 1. No. 2, 3. Two, 3. No, it should be 2, 3. Oh, sorry, here is my mistake. I apologize. So it's 2, 3, 2. Okay? How do I know that it's a mistake? Because 2, 3, 2 is 10, and then 2, 2, 3 is a minus 10. So when you calculate, the result should have been 0. So this way I can write everything. So it's going to be the third one. Both of them are 0. Minus 0 plus 0, minus 7 plus 7, minus 12 plus 12, 8 minus 8, 0 minus 0, and 7 minus 7. Okay? And so you obtain a 0. It's a 0 matrix. It's a coincidence, again? No. Because if you take the curl of a matrix that is actually the gradient of a vector, again, it is equal to 0. So the curl of the gradient of a scalar function is 0. The curl of the gradient of a vector function is also 0. So the curl of any gradient eventually is going to be a 0. Okay. So before, since I made a mistake with one entry, let me just make sure that all the entries here are written correctly for your reference. So this looks like a 3, it's a 1. Okay, so that apparently was the only error. Okay. Which one? Please, English.
The second.
Just on time. Questions? We will need the curl. Specifically, we need this identity. That's why we define the curl. Okay? But when the time comes, eventually, you will see that if the need arises to calculate the curl of a matrix, it will not be very lengthy. For instance, this was rather short. It will be like that. Okay? So the actual application is rarely going to be complicated. Okay. So again, if no further questions, let's meet next time. Okay? I suggest that you review all of these operations because we will now start making use of them without, again, defining every time. Okay? So see you next time.